Hello, this is part 2 of a series, a set of videos that I prepared on the topic of modal analysis. Like I said, at first we were going to look at continuous systems just sort of in general, and we saw some cases of some real world cases. Well, first we looked at some simple fixed beam, cantilever beam, then some ship modal shapes, then some modal shapes of a C-130 aircraft. Now, what I want to do is leave the topic of continuous systems, which deserve more attention, but I want to first focus on discrete systems, or lump mass systems as they're called. These are a little bit easier to analyze, and so in my opinion, what we should do is analyze these first and then go to continuous systems. The first system that I want to look at is a simple system, 2 carts with a spring connection in between them. Now, this looks very artificial, obviously, but this could represent, for instance, 2 railroad cars that are hooked together with some type of flexible connection. So even though we're not looking at continuous systems, there are many real lump mass systems in the real world, or even continuous systems that approximate lump mass systems. And so this is not just an academic exercise, this is an important exercise for understanding real world systems. These masses are connected by a spring, and I have named this in my book, Control Systems Engineering, A Practical Approach. In Chapter 3, there's a procedure given for developing the equations of motion for, well, all sorts of systems, but one of which are MCK systems, or MK systems, which are mass damping spring systems, or just mass spring systems if you have no damping. I'm not going to go over that procedure here, but I've used that actually to derive the equations of motion for this system here. And basically, since I have 2 masses, I'm going to have 2 equations. It's not forced, so this is a free system. So if you look at my equations here, they're 0 on the right-hand side. And if I develop those equations, then if I use that methodology, I come up with these 2 equations. And once I have the 2 equations, I can put them into the matrix formulation, which is what I do here. Let's see, I can blow this up a little bit, I suppose. Yeah, that makes it easier for the internet audience to see. So I've simply just gotten these equations and organized them into this matrix format. So anyway, what I want to do now is, once I have these equations and I've assigned values to them, then I want to go to the MATLAB-like simulation program, open source simulation program, Octave, and see how this system is going to behave. So let me turn Octave on. I already have it turned on. And I'll make it so that I can actually see. Let's put Octave up here, and then let me put this down here so I can see what I have for my values here. So what I can do is I can define my mass matrix. I'll call it big M equals, and actually I should probably blow the Octave up too. Let me make it a little bit bigger so that more people can see it without going blind. I thought I could blow this window up. Well, it looks like I can't, unfortunately. Boy, I was able to do that before. Well, let's see here. Well, I'm not going to lose, I don't want to get involved in trying to figure out how to magnify this online, so I'll just talk and say what I'm typing. Big M is equal to, and then there's a set of brackets. Let me go back and get my values there. Looks like I have 10,000. Let me make this smaller so we can see better. So in my upper left-hand corner, I'm going to have 10,000, comma, and then a 0, and then a semicolon, 0, and then another 10,000. So that's my mass matrix. And my stiffness matrix is big K equals, brackets open, and these are 10,000 also. These are just kind of randomly picked numbers. But they show the principle. Oh, that should be a negative for the off-diagonal elements. Let me change that. So it's 1,000 and then negative 1,000. And then in the lower left-hand corner, we have negative 10,000. Sorry, I said 1,000. It's 10,000. And then 10,000 positive. And there's my stiffness matrix, close brackets. So I have my mass matrix and my stiffness matrix. Now, what happens is we need to combine those into what I call an Eigen Matrix, where basically, as we know, in vibrations with a single degree of freedom system, omega n squared, the natural frequency squared, is equal to k over m. Well, we form the matrix that's the counterpart to that for a multi-degree of freedom system like this, and basically, so I'll call it Eigen Matrix. You can call it whatever you want. And it's simply, well, I'll tell you what, before I do that, I know what the answer is going to be. Before I invert any matrix, it's a good idea to check its determinant. So I'm going to invert the mass matrix because it's square root of k over m, or k over m is the natural frequency squared. So I want to check and make sure that I can invert the mass matrix. So I take the determinant of the mass matrix. Oh, and it's not 0, so that means that I can invert it. And now I will form the Eigen Matrix. Eigen Matrix, probably a better name for it. And it's just going to be m raised to the minus 1 power times k. And yes. Interesting. So we have something that's all ones, and that's because of the values that I picked. But now what we need to do is we need to get the eigenvalues and the eigenvectors out of this matrix. So there's a function for doing that, and in Octave, and it's called eigens, I-G-E-N-E, eigens, no, eigs, sorry. And then we simply put in that Eigen matrix. Now, I may be doing this wrong. I may have to come and do it again because I've kind of forgotten the format. Okay, what I'm getting here, as a result, I can tell as I'm getting the eigenvalues, or at least that's what I suppose that they are. I think that what I need to do, let me try this and then I'll look it up if this doesn't work. You can put in the V, which is the eigenvectors, and then D, which are the eigenvalues, and then set that equal to, so that's the output, Eigen matrix. Because what I want is not just the eigenvalues, I want the eigenvectors too. Voila, that did what I wanted it to do. Okay, now I tell you what, so that we can see this clearly, what I'm going to do is blow it up, and I'm going to trick it into blowing it up. I'm just going to take a screenshot of it. Let's see here. This isn't everything that I have, but it's enough. Okay, and then I think I can blow this up. Let's see. It's not letting me blow it up. Man, I'm having a hard time with this. Well, I think it's a little bit bigger anyway. All right, so let's talk about our results here. I'll just blow it up full screen. So I formed my Eigen matrix, and again, what that was, it's the inverse of the mass matrix multiplied by the K matrix. And that gave me this Eigen matrix. And this contains the eigenvalues and eigenvectors of the system. Now, I'm not going to go into the Eigen problem. That's a separate mathematical topic that I'm not going to cover here. But what I do want to say is you do need the eigenvalues, because the eigenvalues, and the eigenvalues are 2 and 0, those are the squares of the natural frequencies. So for one thing, like I said before on the first video, the system has more than one frequency of oscillation, and it has more than one mode shape. So we can see what the frequencies are, and we can see what the mode shapes are. Okay, I'm over 10 minutes, so I'm going to stop this and we'll pick it up here. I'll figure out a way to make that big, and then I'll be back.